A lemon-shaped planet, orbiting a dead star, with an atmosphere made of pure soot and diamonds. That is not science fiction. That is exactly what the James Webb Space Telescope just found hiding 750 light-years away from Earth. And honestly, the scientists who discovered it had no idea what they were looking at. Their exact words were, and I quote, "What the heck is this? If that does not send a chill down your spine, what comes next definitely will." Before we go any further, if you enjoy journeys through the most bizarre corners of the universe, do me a quick favor. Hit that like button and subscribe to the channel. It helps more than you know, and it keeps content like this coming your way. Now here is where things get really unsettling. This planet should not exist. Not according to anything we know about how planets form. Not according to any model we have ever built. Not according to any theory that has ever been published in any scientific journal anywhere in the world. Every single pathway scientists have come up with to explain how a planet could come to be, this one breaks all of them. Every single one. And that is not just me being dramatic. The lead researcher on this discovery, a man named Michael Zhang from the University of Chicago, said it himself. He said it seems to rule out every known formation mechanism. Think about that for a second. We have been studying planets for hundreds of years. We have catalogued thousands of worlds beyond our solar system. We have built supercomputers that can simulate the birth and death of entire star systems. And yet, when we pointed the most powerful space telescope ever created at this one single planet, everything we thought we knew fell apart. So what exactly is going on out there? What is this planet? Why is it shaped like a lemon? Why does it have an atmosphere unlike anything ever observed on any world in the entire history of astronomy? And why are some scientists calling it the most disturbing discovery James Webb has ever made? Let me take you through this step by step, because once you understand what we are dealing with, you will never look at the night sky the same way again. Let us start with the basics. The planet is called PSR J2322-2650b. That is a mouthful, I know. So from here on out, let us just call it PSR for short. But the name actually tells us something important. The PSR part stands for pulsar. That means this planet does not orbit a normal star like our sun. It orbits a pulsar. And if you do not know what a pulsar is, hold on tight, because this is where things start to get wild. A pulsar is what happens after a massive star dies. And when I say massive, I mean truly enormous. We are talking about a star that was at least 10 times heavier than our sun. When a star like that runs out of fuel, it does not just quietly fade away. It explodes. It detonates in one of the most violent events in the entire universe. We call that a supernova. And during that explosion, the outer layers of the star are blown away into space at incredible speeds. But the core of the star, the very center of it, does not get blown apart. Instead, it collapses in on itself. All of that mass, all of that material, gets crushed down into a ball that is roughly the size of a city. Imagine taking something that weighs more than our entire sun and compressing it into a sphere about 12 miles across. That is a neutron star. And a pulsar is a special kind of neutron star, one that spins, and it does not just spin slowly. The pulsar that this planet orbits completes nearly 300 rotations every single second. Let that sink in. 300 times per second. That is 18,000 rotations per minute. And as it spins, it shoots out beams of electromagnetic radiation from its magnetic poles. Those beams sweep across the universe like the light from a cosmic lighthouse. Every time one of those beams happens to point in our direction, we detect a pulse. That is where the name pulsar comes from. Now imagine being a planet in orbit around something like that. This is not a warm, gentle star like our Sun, giving off a nice, comfortable amount of light and heat. This is a dead star, a collapsed remnant of something that used to be enormous. It is only about 12 miles wide, but it has the mass of the entire Sun packed into that tiny space, and it is spinning so fast that it blasts out gamma rays and high-energy particles in every direction. That is the neighborhood this planet calls home. And it gets worse. PSR does not orbit its pulsar at a comfortable distance. Our Earth sits about 93 million miles from the Sun. This planet sits just 1 million miles from its pulsar. 1 million miles. That is less than 1% of the distance between Earth and the Sun. It is so close that the gravitational pull from the pulsar is absolutely crushing. And because of that incredible gravitational force, the planet is not even round. It has been stretched and pulled and warped into the shape of a lemon. Think about that image for a second. A giant planet, roughly the same mass as Jupiter, being squeezed and deformed by the gravity of a dead spinning star until it looks like a piece of fruit. The equatorial diameter of this planet is about 38% wider than its polar diameter. On Earth, the difference between our equatorial and polar diameters is only about 0.3%. So this planet is being stretched more than 100 times more than Earth is. That is how intense the gravitational forces are out there. And because it is so close to the pulsar, this planet whips around its star incredibly fast. One full orbit, 1 full year on this planet, takes only 7.8 hours. Think about what that means. On Earth, a year is 365 days. On this planet, a year is less than a single work shift. You could experience an entire year during a long nap. By the time you wake up, a whole new year has started. But the orbit is not even the strangest part. It is the atmosphere. And this is where the discovery goes from fascinating to genuinely disturbing. When scientists pointed the James Webb Space Telescope at this planet, they expected to find certain things. Certain molecules, certain chemicals, the kinds of things we typically see in the atmospheres of other planets. Things like water vapor, methane, carbon dioxide, hydrogen, the usual suspects. The building blocks that show up again and again across thousands of exoplanets we have studied. But that is not what they found. Not even close. Instead of the normal molecules we expect to see on an exoplanet, the researchers saw molecular carbon, specifically something called C2 and C3. Those are forms of carbon that exist as pairs and triplets of carbon atoms bonded together. And here is the thing. Those forms of carbon can only remain detectable if there is almost no oxygen and almost no nitrogen present. That means this planet's atmosphere is almost completely devoid of two of the most common elements we find on other worlds. No oxygen, no nitrogen, no water vapor, no methane, no carbon dioxide. Just helium and carbon, an atmosphere of helium and soot that has never been seen before, not on any planet, not anywhere in the universe. This is a completely new type of planetary atmosphere. Michael Jang put it simply. He said this is a new type of planet atmosphere that nobody has ever seen before. And the team member Peter Gao from the Carnegie Earth and Planets Laboratory described the moment they first saw the data. He said he remembered their collective reaction was, "What the heck is this? It is extremely different from what we expected." Now here is where it gets even more eerie. Up near the top of the atmosphere, where conditions are a bit cooler, those carbon molecules form clouds. But these are not clouds like anything you have ever seen on Earth. These are clouds of soot. Pure carbon soot floating through the air of this bizarre alien world. And as you go deeper into the atmosphere, where the pressure and temperature increase dramatically, something remarkable happens. That carbon gets compressed, squeezed, crushed under immense pressure. And when carbon is compressed under enough pressure, it forms diamonds. So let me paint this picture for you clearly. This planet has an atmosphere made of helium and carbon soot. It rains diamonds. It is shaped like a lemon. It orbits a dead star that spins 300 times per second, and a full year lasts less than 8 hours. If someone wrote this in a science fiction novel, you would say it was too crazy to be believable. But it is real. It is out there right now, 750 light years away, and we just found it. But the discovery itself is only part of what makes this so disturbing. The real problem, the thing that has scientists genuinely worried and confused, is that nobody can figure out how this planet came to exist in the first place. Let us think about this logically. There are basically a few ways a planet can form. The most common way is the same way the planets in our solar system formed. You start with a big cloud of gas and dust floating in space. That cloud starts to collapse under its own gravity. As it collapses, it flattens out into a spinning disk. The center of the disk becomes a star, and the leftover material in the disk gradually clumps together to form planets. This is called the core accretion model, and it explains how most of the planets we know about came to be. But that model does not work here. The composition of this planet is completely wrong. Normal planets formed from disks of gas and dust have specific chemical signatures. They contain a mix of elements that reflects the composition of the cloud they formed from. Things like hydrogen, oxygen, nitrogen, carbon, silicon, iron, a diverse mix of the elements that make up the periodic table. But PSR has an atmosphere dominated by helium and carbon. Almost nothing else. That is not what you get when a planet forms from a normal disk of material around a star. Okay, so maybe it did not form like a normal planet. Maybe it formed through a different process. The system this planet lives in is what astronomers call a black widow system. That name comes from the black widow spider, which is famous for consuming its mate after mating. In a black widow pulsar system, you have a rapidly spinning pulsar paired with a small companion. Over time, material from the companion streams onto the pulsar. This extra material causes the pulsar to spin faster and faster, which powers up a strong wind of radiation. That wind and radiation then bombard the companion, slowly stripping away its outer layers. The pulsar literally consumes its partner piece by piece. So maybe this planet started out as a star. Maybe it was a normal stellar companion that got eaten alive by the pulsar over billions of years, stripped down until only this planetary mass remnant was left. That would be a dramatic origin story, right? A star that was slowly devoured until it became a planet. But here is the problem with that explanation too. When you strip the outer layers off a star through nuclear processes, you do not get pure carbon. Nuclear physics does not produce an atmosphere of pure carbon. The nuclear reactions that power stars create a mix of elements, not a single pure element. Michael Jang addressed this directly. He said, "Did this thing form like a normal planet? No, because the composition is entirely different. Did it form by stripping the outside of a star, like normal black widow systems are formed? Probably not, because nuclear physics does not make pure carbon. So it did not form like a planet. It did not form like a stripped star. And no other known formation mechanism explains it either. That is the disturbing part. This planet exists We can see it, we can study it, we can measure its atmosphere, but we cannot explain how it got there. It should be impossible. And yet, there it is. There is one more mind-bending detail about this planet that makes it even stranger. The James Webb Space Telescope was actually able to study this planet in unusual detail. And the reason why is kind of poetic. You see, the pulsar this planet orbits emits mostly gamma rays and other high-energy radiation. Those are types of light that are invisible to Webb's infrared cameras. So when Webb looks at this system, it cannot see the star at all. The star is essentially invisible to the telescope, but the planet is not. The planet glows in infrared light because it is heated by the radiation from the pulsar. So Webb can see the planet clearly, without the blinding glare of the star getting in the way. Maya Belesnay, a graduate student at Stanford University who worked on modeling the planet's shape and orbit, explained this perfectly. She said this system is unique because we are able to view the planet illuminated by its host star, but not see the host star at all. So we get a really pristine spectrum, and we can better study this system in more detail than normal exoplanets. That is an incredible stroke of luck. It is like trying to study a firefly next to a searchlight, except in this case, the searchlight happens to be shining in a color that your eyes cannot see. So the firefly becomes the only thing visible. It allowed the scientists to get an incredibly detailed picture of what this planet is actually like. And what they found is that the planet's atmosphere is not just unusual, it is actively hostile. The gamma radiation from the pulsar heats the atmosphere to temperatures around 1900 Kelvin. That is roughly 1600 degrees Celsius, or about 2960 degrees Fahrenheit. And that is far higher than what you would expect if the planet were being heated by normal starlight alone. The pulsar is essentially cooking this planet with high-energy radiation, superheating its atmosphere to temperatures that would melt most metals. But wait, there is something even more bizarre happening with the atmosphere. Researchers discovered that the entire atmosphere of this planet is rotating. That is not unusual on its own. Atmospheres rotate on many planets, including Earth. But the direction of the rotation is what caught everyone off guard. The atmosphere of PSR is rotating in the opposite direction of the planet itself. The planet spins one way, locked to its orbit around the pulsar, moving eastward. But the atmosphere races around the planet going westward at tremendous speed. Nobody fully understands why. Imagine standing on this planet, if you somehow could. Beneath your feet, the ground would be moving in one direction, but the sky above you, the sooty carbon atmosphere filled with diamond-forming clouds, would be rushing past in the opposite direction. Like the planet and its own atmosphere are fighting each other. Two forces pulling in opposite directions on a world that should not exist in the first place. Roger Romani, one of the team members from Stanford and the Kavli Institute for Particle Astrophysics and Cosmology, is one of the world's foremost experts on black widow systems. He has spent his career studying these extreme partnerships between pulsars and their doomed companions. And even he found this planet to be remarkably strange. He proposed one fascinating phenomenon that might be happening deep within the planet's interior. As the companion cools down over time, the mixture of carbon and oxygen in the interior starts to crystallize. In other words, the inside of this planet might be slowly solidifying into a giant crystal. A crystal made of diamonds. So let us put all of these pieces together. What we are looking at is a planet the mass of Jupiter, squeezed into a lemon shape by the gravity of a dead spinning star. Its atmosphere is made of helium and carbon soot. It rains diamonds. The air moves in the opposite direction of the ground. It completes a full orbit in less than 8 hours. It is blasted by gamma radiation that heats its atmosphere to thousands of degrees. Its interior might be crystallizing into diamond. And no known scientific theory can explain how it formed. That is not just weird, that is deeply, fundamentally disturbing, because it means our understanding of how planets work, how they form, how they evolve, has a massive hole in it. A hole big enough to fit a lemon-shaped diamond planet through. But here is the thing. This planet is just the beginning, because the James Webb Space Telescope is not done making disturbing discoveries, not by a long shot. In fact, around the same time this diamond planet was making headlines, Webb was also studying another world that turned out to be equally impossible. A planet that scientists are calling a hell world. A broiling inferno covered in a global ocean of molten rock. A planet that should be a bare, airless hunk of stone, but instead is wrapped in a thick atmosphere that defies everything we thought we knew. That planet is called JWST 561b. And if the diamond lemon planet represents one kind of cosmic nightmare, this one represents a completely different kind of horror. JWST 561b is what scientists call an ultra-short period super-Earth. It is a rocky planet, roughly 1.4 times the size of Earth and about twice Earth's mass. It orbits a star that is about 280 light-years away from us, in the constellation Sextans. And when I say it orbits closely, I mean absurdly, ridiculously, insanely closely. This planet sits at just 1/40th the distance between Mercury and our Sun. Mercury is already the closest planet to the Sun in our solar system. And JWST 561b is 40 times closer than that. At that distance, the planet completes a full orbit in just 10.56 hours, less than half a day on Earth. And because it is so close to its star, it is tidally locked. That means one side of the planet permanently faces the star, baking under constant, relentless radiation. The other side faces away, trapped in eternal darkness. There is no sunrise and no sunset on this world. Just an endless scorching day on one side and an endless frozen night on the other. Now here is where the expectation comes in. Based on everything we know about planets in this situation, JWST 561b should be a bare rock, completely airless. The intense radiation from its star should have blasted away any atmosphere long ago. Planets this small, this hot, and this close to their stars simply do not hold on to their atmospheres. The energy from the star gives gas molecules enough speed to escape the planet's gravity. Over billions of years, any atmosphere the planet might have started with should have been completely stripped away. And there is an additional wrinkle that makes this even more extreme. JWST 561b orbits a very old star, about twice as old as our own Sun. That means this planet has been sitting in this hellish position for an incredibly long time. 10 billion years of constant bombardment. 10 billion years of intense radiation trying to blow away any gases clinging to the planet's surface. There is simply no way a planet this old, this small, and this close to its star should have any atmosphere at all. But when the James Webb Space Telescope turned its infrared eyes on JWST 561b, it found something that nobody expected. The planet's dayside temperature was wrong, way wrong. Here is what I mean. If JWST 561b were a bare rock with no atmosphere, scientists could calculate exactly how hot its dayside should be based on the amount of radiation it receives from its star. That calculation said the temperature should be approaching 4,900 degrees Fahrenheit. That is about 2,700 degrees Celsius. Hot enough to melt most rocks. hot enough to turn the entire surface into a bubbling ocean of liquid stone. And scientists fully expected the planet to be at exactly that temperature. Just a bare, molten rock getting blasted by its star. But when Webb measured the actual temperature, it came back at only about 3,200 degrees Fahrenheit. About 1,800 degrees Celsius. Now that is still insanely hot. That is still hot enough to melt most materials on Earth. But it is significantly cooler than it should be. Almost 2,000 degrees Fahrenheit cooler than expected. That is a massive discrepancy. And in science, when your measurements do not match your predictions by that much, it means something fundamental about your assumptions is wrong. The research team, led by Johanna Teske from the Carnegie Science, Earth and Planets Laboratory, tested multiple explanations. Maybe the surface was made of some unusual type of rock that radiated heat differently. Maybe the magma ocean on the surface was circulating heat somehow. Maybe there was a thin layer of rock vapor hovering above the molten surface. They tested all of these possibilities, and none of them could explain the temperature difference. None of them even came close. There was only one explanation that fit the data. TOI 561b has a thick atmosphere, not a thin wisp of gas, not a faint haze, a substantial, dense blanket of gases sitting on top of a global ocean of molten rock, an atmosphere rich in volatile chemicals, chemicals like water vapor and other molecules that interact strongly with light. Think about how bizarre this is. A planet that is 40 times closer to its star than Mercury is to the Sun. A planet that has been bombarded by radiation for 10 billion years. A planet that every model says should be completely, utterly, irrevocably airless. And yet it has a thick atmosphere. That should be impossible. And yet the data says it is real. Angélie Piet, an astronomer at the University of Birmingham who worked on the study, explained what they think is happening. She said they really need a thick, volatile, rich atmosphere to explain all the observations. Strong winds would cool the day side by transporting heat over to the night side. Gases like water vapor would absorb some wavelengths of near-infrared light emitted by the surface before they make it all the way up through the atmosphere. It is also possible that there are bright silicate clouds that cool the atmosphere by reflecting starlight. Silicate clouds. Let that sink in. On Earth, our clouds are made of water droplets. On this planet, the clouds might be made of silicates, the same mineral family that makes up most rocks on Earth. Sand clouds, rock clouds, floating in the sky of a planet covered in a global ocean of lava. And here is what is truly wild. The reason this planet can hold onto its atmosphere despite all that radiation is because of the magma ocean itself. Tim Lichtenberg, an astronomer from the University of Groningen in the Netherlands, proposed that there is a constant exchange happening between the planet's molten surface and its atmosphere. Gases escape from the magma into the atmosphere. But at the same time, the magma ocean is pulling gases back down into the interior. It is a cycle, a feedback loop. The planet's own molten surface is feeding its atmosphere from below, replacing the gases that get stripped away by stellar radiation. Lichtenberg put it in the most vivid terms possible. He said this planet must be much, much more volatile rich than Earth to explain the observations. He called it, and these are his exact words, really like a wet lava ball. A wet lava ball. A planet with a permanent ocean of molten rock on its surface, with a thick atmosphere of volatile gases being constantly recycled through the magma, with silicate clouds floating overhead, and temperatures that can melt stone. That is TOI 561b, and nobody can fully explain how it maintains this atmosphere after 10 billion years of punishment. What is really exciting, Teskey said, is that this new data set is opening up even more questions than it is answering. And that statement right there tells you everything you need to know about where we are in our understanding of the universe right now. Every time we look closer, every time we build a better telescope, every time we gather more data, we find things that do not make sense. Things that break our models. Things that force us to start over and rethink everything from scratch. And those two planets, the Diamond Lemon World and the Lava Hell planet, are just the latest examples. Because the James Webb Space Telescope has been revealing disturbing planet after disturbing planet, and each one is more unsettling than the last. Take WASP 121b, for instance. Also known by its official name Tylos, this planet sits about 858 light-years from Earth. It is what astronomers call an ultra-hot Jupiter, a massive gas giant planet like our own Jupiter, but parked so close to its parent star that it completes a full orbit in just 30 hours. And the radiation from that star heats its atmosphere to around 4,200 degrees Fahrenheit. That is 2,300 degrees Celsius. For context, that is hot enough to melt platinum, hot enough to vaporize lead, hot enough to turn iron into a gas. But the temperature is not even the most disturbing thing about WASP 121b. What really shocked scientists was what they found when they used the James Webb Space Telescope to study the planet over the course of an entire orbit. For the very first time, they were able to track the gases leaking from an exoplanet through its complete journey around its star, and what they discovered was something that nobody had predicted. WASP 121b has two enormous tails. Not one, two, and they are made of helium gas, streaming away from the planet like the tails of a comet. But these tails are not small. They stretch across nearly 60% of the planet's entire orbit. That is an absolutely staggering scale. Imagine a planet leaving a trail of gas behind it that covers more than half of its path around its star. That is what is happening here. One of the tails trails behind the planet, pushed back by the radiation and stellar wind from the parent star. That makes sense. That is what you would expect. When a planet is losing its atmosphere, the gas gets blown backward by the star's radiation, just like the tail of a comet always points away from the sun. But the second tail is the one that baffled everyone. It curves ahead of the planet, in front of it, leading the way like a ghostly banner waving in the direction the planet is heading. Scientists think this leading tail is being pulled forward by the gravity of the star itself, dragging the escaping helium inward. So you have this massive gas giant planet, hotter than most stars, leaking its atmosphere from both ends, leaving twin helium tails that span most of its orbit. It is like watching a planet slowly die in real time, being unraveled by its own star. And the scientists studying it openly admitted that the twin tail structure was not something their models had predicted. They are only beginning to discover the true complexity of these worlds. And that complexity goes even deeper. Because another team of scientists used Webb to create something that had never been done before in the entire history of astronomy. They built the first ever three-dimensional temperature map of a planet outside our solar system. And the planet they chose for this groundbreaking achievement was another ultra-hot Jupiter called WASP 18b. WASP 18b sits about 400 light-years from Earth. It has roughly 10 times the mass of Jupiter and completes an orbit around its star in just 23 hours. Its temperatures reach nearly 5,000 degrees Fahrenheit. That is so hot that water molecules literally get torn apart, not evaporated, destroyed. The water vapor in the planet's atmosphere is broken down into individual hydrogen and oxygen atoms by the sheer intensity of the heat. Using a technique called three-dimensional eclipse mapping, the team analyzed data from Webb's near-infrared imager and slitless spectrograph instrument. They measured tiny changes in the planet's brightness as it passed behind its star, and by looking at those changes in many different colors of light, they were able to figure out the temperature at different locations across the planet's surface and at different altitudes in its atmosphere. What they found was a planet divided into distinct thermal regions. The hottest spot on the planet is a circular region on the side that permanently faces the star, that is surrounded by a cooler ring at the edges. And in that hottest region, the temperatures are so extreme that water vapor is being ripped apart. This was something scientists had theorized about for years, but the three-dimensional map confirmed it through direct observation for the first time. Ryan Challoner, the lead author of that study, described the significance. He said they can now begin to view exoplanet atmospheres in 3 dimensions, much like how telescopes once revealed Jupiter's storms and cloud bands. That might sound like a technical achievement, and it is, but it also means we are now seeing the weather on alien worlds in ways we never could before. And the weather on these worlds is nightmarish. Imagine a planet where one side is perpetually blasted by radiation so intense it rips water apart at the molecular level, where the other side never sees light, where the temperature difference between the day and night sides drives winds at thousands of miles per hour, where the very chemistry of the atmosphere changes depending on whether you are standing in daylight or darkness. That is not a planet you would want to visit. That is a planet you would want to run from. And WASP 18b is just one example of what these ultra-hot Jupiters are like. Consider WASP 76b, one of the most famous extreme exoplanets ever discovered. This planet sits about 640 light-years from Earth in the constellation Pisces. It has about the mass of Jupiter, but is nearly twice as wide, puffed up by the tremendous radiation it receives from its star. It completes an orbit in less than 2 Earth days. The day side of WASP 76b reaches temperatures above 4,350 degrees Fahrenheit. That is 2,400 degrees Celsius. At those temperatures, metals vaporize. Iron, one of the strongest and most familiar metals in our everyday lives, turns into a gas on the day side of this planet. Iron vapor fills the atmosphere, swirling and churning in the superheated air. But here is the horrifying part. The night side of WASP 76b is cooler. Not cool by any human standard, mind you. It is still roughly 2,700 degrees Fahrenheit on the night side, but that is cold enough compared to the day side for something terrifying to happen. Strong winds, blowing at speeds of up to 18,000 kilometers per hour, carry the iron vapor from the scorching day side over to the cooler night side. And when that iron vapor reaches the night side, the temperatures drop just enough for the iron to condense. It turns from a gas back into a liquid, and it falls. It rains iron on WASP 76b, actual liquid drops of iron falling from the sky like rain, not water, not ice, iron. Molten, glowing, red-hot drops of iron falling through a superheated atmosphere of vaporized metal. David Ehrenreich, the astronomer from the University of Geneva who led the original study of this planet, said it perfectly. He said one could say that this planet gets rainy in the evening, except it rains iron. And the evidence for this comes from careful observations of the planet's atmosphere. When scientists looked at the evening side of the planet, where the transition from day to night occurs, they found a strong signature of iron vapor. But when they looked at the morning side, where the transition from night to day occurs, The iron was gone. It had condensed and fallen out of the atmosphere overnight, literally rained down into the depths of the planet. Now, because WSP-76b is a gas giant, there is no solid surface for that iron rain to land on. The drops of liquid iron sink deeper and deeper into the planet's atmosphere, falling into hotter and hotter layers until they eventually vaporize again. And then the cycle starts over. Iron evaporates on the day side, gets blown to the night side by howling winds, condenses into rain, falls deeper into the atmosphere, heats up, and evaporates again. An endless, nightmarish cycle of iron weather. More recent observations from the European Space Agency's JWST telescope even detected hints of a strange phenomenon called a glory effect in WSP-76b's atmosphere. A glory is a rainbow-like arrangement of colorful concentric rings of light that occurs under very specific conditions. We sometimes see glories on Earth, typically from airplanes when they look down at clouds below. Venus has them too, but finding evidence of a glory on an exoplanet 640 light-years away, a planet where it rains molten iron, is something nobody expected. If confirmed, it would mean that despite all the chaos and violence happening on this world, there are also hauntingly beautiful optical effects dancing through its atmosphere. Beauty and horror existing side by side on the same impossible world. These are the kinds of planets the James Webb Space Telescope is showing us. Worlds that make our most creative science fiction look tame by comparison. Worlds that challenge the very foundations of what we think we understand about planetary science. And the thing is, we are still in the early days. Webb launched on Christmas Day in 2021 and began its science operations in 2022. In just a few years, it has already transformed our understanding of the universe. It has shown us planets we could not have imagined, atmospheres we did not think were possible, weather systems that belong in nightmares, and formation pathways that break every model we have. But let me bring us back to the planet that started this whole conversation. The one that scientists say is the most disturbing of them all. PSR, the Diamond Lemon Planet, orbiting a dead star. Because there is still more to this story. There are layers to this discovery that go beyond just the planet itself. Layers that touch on some of the biggest questions in all of science. The first question is about the nature of this object. Is it really a planet, or is it something else entirely? The International Astronomical Union officially classifies PSR as an exoplanet. Its mass is about 80% that of Jupiter, which puts it squarely in the planetary range. But its composition and its origin story do not match anything we associate with planets. It has an atmosphere that looks nothing like any planet's atmosphere. It orbits a type of star that most planets cannot survive around, and it may have originally been a star itself, stripped down to its current state over billions of years. Michael Jang asked the key question directly. Did this thing form like a normal planet? No, because the composition is entirely different. Did it form by stripping the outside of a star? Probably not, because nuclear physics does not make pure carbon. So what is it? It exists in a strange no-man's land between planet and star. Too small to be a star. Too weird to be a normal planet. A cosmic orphan with no clear family tree. This ambiguity is part of what makes it so disturbing. In science, we like to categorize things. We like to put them in neat boxes. Stars go in one box. Planets go in another. Brown dwarfs, those failed stars that are too small to sustain nuclear fusion, go in a third box. But PSR does not fit in any of these boxes. It is something new, something we do not have a category for. And when nature shows us something that does not fit our categories, it usually means our categories are wrong. The second big question this discovery raises is about the history of this system. How did this planet end up where it is now? We know it is part of a black widow system, where the pulsar is slowly consuming its companion, but the details of how the system evolved over time are murky at best. At some point in the distant past, there was a massive star and a smaller companion orbiting each other. The massive star exploded as a supernova, leaving behind the neutron star that became the pulsar. But the companion survived the explosion somehow. Over billions of years, the pulsar spun faster and faster as it accreted material from the companion. The companion got smaller and smaller, until eventually what was left was this strange planetary mass object with its impossible carbon atmosphere. But what was the companion before all of this happened? Was it a normal star, a white dwarf, something else entirely? And how did the process of being stripped by the pulsar produce an atmosphere of pure carbon when nuclear physics says it should not? These questions do not have answers yet, and that is both exciting and deeply unsettling. The third question is perhaps the most profound of all. If this planet can exist despite breaking every known formation model, what else is out there that we have not found yet? What other impossible worlds are waiting to be discovered? The universe has been around for 13.8 billion years. There are hundreds of billions of galaxies, each containing hundreds of billions of stars, many of which have planets orbiting them. The total number of planets in the observable universe is estimated to be in the trillions, and we have studied only a tiny, tiny fraction of them. If the first few thousand exoplanets we have examined include a lemon-shaped diamond world orbiting a dead star, a lava planet with an impossible atmosphere, a world where it rains molten iron, and a gas giant leaving twin helium tails across its orbit, what horrors and wonders are we going to find when we start looking at millions of planets? What about when we can study billions? The universe is clearly far stranger than our imaginations can contain, and the James Webb Space Telescope is proving that every single day. Let us go deeper. Let us talk about what these discoveries mean for our understanding of the universe as a whole. Because these are not just interesting individual stories. They represent a fundamental shift in how we think about what is possible in the cosmos. For decades, planetary science has operated under a set of assumptions. We assume that planets formed in predictable ways. We assume that their atmospheres followed certain rules. We assume that the planets in our own solar system, while diverse, represented a reasonable sample of what you could find out there. Rocky planets close to the star, gas giants farther out, atmospheres made of familiar gases, weather patterns that could be explained by basic physics, neat, tidy, understandable. The James Webb Space Telescope has torn that assumption to shreds. Consider what we have learned just from the discoveries we have talked about so far. We learned that a planet can exist with an atmosphere made entirely of helium and carbon soot, something that has never been seen before and that no model predicted. We learned that a planet can maintain a thick atmosphere despite being bombarded by radiation for 10 billion years, something that every existing model said was impossible. We learned that planets can be shaped like lemons by the gravity of dead stars. We learned that iron can rain from alien skies. We learned that entire atmospheres can leak into space, leaving ghostly trails that stretch across most of a planet's orbit. None of these things were in the textbooks 5 years ago. None of them were predicted by the models we had built, and all of them were discovered by a single telescope in just a few years of operation. If this is what we find in the very beginning, Imagine what the next decade of Webb observations is going to reveal. But let us get even more specific about why the Diamond Lemon Planet is considered particularly disturbing, even among all these other incredible discoveries. It comes down to a concept that scientists call formation pathways. Every planet we have ever studied before can be traced back to some kind of formation pathway, a sequence of events and processes that explains how the planet came to be. Even the weirdest planets we had found before this one could be at least partially explained by existing theories, even if those explanations were incomplete or uncertain. PSR is the first planet that appears to rule out all known formation pathways entirely. Not just some of them, all of them. That has never happened before. It is one thing to find a planet that is hard to explain. It is entirely another to find a planet that seems to be genuinely unexplainable with our current understanding of physics and astronomy. When Zhang said it seems to rule out every known formation mechanism, that was not hyperbole. That was a carefully considered scientific statement published in a peer-reviewed journal. The Astrophysical Journal Letters, one of the most prestigious publications in all of astrophysics. These scientists did their homework. They considered every possibility, and they concluded that none of them work. That kind of conclusion is rare in science. Usually, even when something surprising is found, scientists can point to at least one possible explanation, even if it is speculative. But in this case, the team could not even offer a speculative explanation that fully fits the data. The planet's composition is too unusual. Its location is too extreme. Its origin is too mysterious. It exists in a space that our theories simply do not cover. Now, some people might hear that and think, well, it is just one planet, one weird outlier. It does not change the big picture. But that is not how science works. In science, a single unexplainable observation can unravel entire frameworks of understanding. The history of physics is filled with examples of this. A single experiment showing that light always travels at the same speed, regardless of the motion of the observer, led to Einstein's theory of special relativity, which completely overturned our understanding of space and time. A single observation of light bending around the sun confirmed general relativity and changed physics forever. A single unexpected pattern in the cosmic microwave background radiation revolutionized our understanding of the early universe. One anomaly is all it takes. And PSR is not just an anomaly. It is a screaming, lemon-shaped, diamond-raining, counter-rotating atmosphere anomaly that says our understanding of planet formation has serious, fundamental gaps. Now let me take you on a journey through time. Let me tell you the story of how this planet was discovered, because that story itself is fascinating. It all began in 2017. That was when astronomers first detected the presence of something orbiting the pulsar PSR. They were not using the James Webb Space Telescope at that point. Webb had not even launched yet. Instead, they were using radio telescopes to study the pulsar's timing. You see, pulsars are incredibly precise. Their pulses arrive at such regular intervals that they can be used as cosmic clocks. Some pulsars are so precise that they rival the best atomic clocks on Earth. But when astronomers look closely at the timing of pulses from PSR, they noticed something was off. The pulses were not arriving at perfectly regular intervals. They were slightly early sometimes and slightly late at other times. This wobble in the timing could only be explained by one thing. Something was orbiting the pulsar. Something with enough mass to gently tug on the pulsar as it went around, causing those tiny timing variations. From the pattern of the wobble, the astronomers could figure out some basic properties of the companion. It had a mass of about 80% of Jupiter's mass. It orbited the pulsar once every 7.8 hours, and it was extremely close to the pulsar. That was all they could determine from the radio data alone. They knew something was there, but they could not see it. They could not study its atmosphere. They could not determine its composition. It was just a ghost, a shadow inferred from tiny perturbations in a stream of radio pulses. For years, that was all we knew. A mysterious companion orbiting a distant pulsar. One entry among thousands in the growing catalogue of exoplanet candidates. Nothing about it seemed particularly special at the time. Black Widow pulsar systems were already known to astronomers. Companions orbiting millisecond pulsars were nothing new. This system was noted, catalogued, and largely set aside while astronomers pursued other targets. Then came the James Webb Space Telescope. Launched on Christmas Day 2021, Webb spent its first few months deploying its massive gold-plated mirror, cooling down to operating temperature, and calibrating its instruments. By mid-2022, it was ready to begin science operations, and it immediately began rewriting the textbooks. Among the thousands of targets that various science teams proposed for Webb observation, someone had the foresight to include PSR in the list, and that decision turned out to be one of the most consequential in the history of exoplanet science. Because when Webb turned its infrared cameras toward this system, it did not just confirm the existence of the companion. It revealed something that nobody could have anticipated. The first thing the researchers noticed was the infrared brightness of the companion. It was glowing, strongly, in infrared wavelengths, and it was varying in brightness as it orbited the pulsar. By carefully tracking how the brightness changed over the course of the 7.8-hour orbit, the team could deduce all sorts of information about the companion, its temperature, its shape, the orientation of its orbit, and that is where the lemon-shaped revelation came from. The brightness pattern could only be explained if the companion was not spherical. It was elongated, stretched along the axis pointing toward the pulsar, pulled into an oblate spheroid by tidal forces, a cosmic lemon. But the real bombshell came when they analyzed the spectrum of the companion's light. A spectrum is like a fingerprint. Every chemical element and molecule absorbs and emits light at specific wavelengths. By spreading out the companion's light into its component colors and looking for the signatures of different molecules, the researchers could figure out what the atmosphere was made of. And that is when the screaming started. Not literally, of course, but scientifically speaking, the spectrum was screaming something that made no sense. The familiar signatures of water vapor were absent. Methane was absent. Carbon dioxide was absent. Hydrogen, the most abundant element in the universe and a dominant component of virtually every gas giant atmosphere ever studied, was not the primary constituent. Instead, the spectrum showed clear signatures of molecular carbon, C2 and C3, diatomic carbon and tricarbon, and helium. That was the moment the researchers looked at each other and said, "What the heck is this?" Because an atmosphere of helium and molecular carbon is something that had never been observed on any world, anywhere, ever. It is not just unusual, it is unprecedented, and the specific forms of carbon they detected, C2 and C3, are only stable in an environment that is almost completely free of oxygen and nitrogen. If oxygen were present, it would react with the carbon and form carbon dioxide or carbon monoxide. If nitrogen were present, it would form other compounds. The fact that C2 and C3 are detectable means that both oxygen and nitrogen are essentially absent from this planet's atmosphere. That is the chemical equivalent of finding a house with no walls. Oxygen and nitrogen are everywhere in the universe. They are among the most common elements. Finding a planet-sized object that has almost none of either is like finding a beach with no sand. It should not be possible. And yet, the data is clear. After the initial shock wore off, the team began trying to figure out what this meant. They ran models. They compared the spectrum to theoretical predictions for different atmospheric compositions. They considered every possible scenario they could think of. And slowly, a picture began to emerge. A terrifying, beautiful, impossible picture. Up high in the atmosphere, where temperatures are relatively cooler, the carbon molecules clustered together to form particles of soot. Pure carbon soot, like the black residue you find inside a chimney. These soot particles form clouds. Thick, dark clouds of pure carbon floating in an alien sky. As you descend deeper into the atmosphere, the pressure and temperature increase. The soot gets compressed tighter and tighter. And at some critical depth, the conditions reach the point where carbon undergoes a phase transition. It stops being soot and starts becoming diamond. The exact depth at which this transition occurs depends on the local temperature and pressure, and the team is still working out those details. But the basic physics is sound. We already know that diamonds form when carbon is subjected to extreme pressure. It happens deep inside the Earth, where diamonds form naturally in the upper mantle. It happens in laboratory settings, where scientists can create artificial diamonds using high-pressure presses. And it almost certainly happens in the atmospheres of our own solar system's giant planets, where scientists have long speculated that it might rain diamonds deep inside Jupiter and Saturn. But on PSR, the process is happening in an atmosphere made almost entirely of carbon. The raw material is everywhere. The pressure is tremendous, and the result is a planet where diamond formation is not just possible, but likely inevitable. Roger Romani, the Black Widow system expert from Stanford, painted a vivid picture of what the interior might be like. As the companion cools down over time, the mixture of carbon in the interior starts to crystallize. The planet's core might be slowly transforming into an enormous diamond crystal, a Jupiter mass diamond shaped like a lemon, orbiting a dead star. Let us pause here and appreciate the sheer scale of what we are describing. This is not a planet with some diamonds in it, the way Earth has a few diamond deposits scattered underground. This is a planet where diamonds might be one of the primary structural components, where the rain is made of diamonds, where the clouds are made of the raw material that becomes diamonds, where the entire interior might be in the process of crystallizing into one massive diamond structure. We are talking about a diamond the mass of Jupiter. That is roughly 318 times the mass of Earth. The amount of carbon involved is staggering beyond comprehension, and all of it orbiting a spinning dead star, being blasted by gamma radiation, with an atmosphere that flows in the opposite direction of the planet's rotation. This is not just the most disturbing planet the James Webb Space Telescope has found. It might be the most disturbing planet in the entire known universe. But even beyond the sheer spectacle of the planet itself, there is a deeper layer of disturbance here, because this discovery forces us to confront a question that scientists have been wrestling with for years, one that gets more urgent with every new exoplanet discovery. That question is simply this: how much do we really understand about the universe? We like to think we have a pretty good handle on things. We have equations that describe gravity, electromagnetism, and the nuclear forces. We have models that can predict the behavior of stars, the formation of galaxies, and the evolution of the universe from the Big Bang to the present day. We have sent spacecraft to every planet in our solar system. We have built telescopes that can see across billions of light years. We have decoded the basic laws of physics and chemistry and used them to build the modern world. And yet, a single planet 750 light years away has stumped us. Our best theories cannot explain it. Our most sophisticated models cannot reproduce it. Our most experienced scientists are scratching their heads and admitting that they simply do not know what is going on. That is humbling, and it is also exciting, because it means there is still so much to learn, so much to discover, so much that the universe is hiding from us, waiting for us to build better telescopes and develop better theories and look more carefully at the data. The story of PSR is not a story of failure. It is a story of nature being far more creative and far more surprising than we ever gave it credit for. Now, let me take this in a slightly different direction, because I want to talk about what these extreme exoplanets, these disturbing worlds, tell us about the range of possibilities in the universe. And I want to connect that to something that affects all of us on a deeply personal level. Think about Earth for a moment, our planet, our home. A world with liquid water oceans, a breathable atmosphere, moderate temperatures, and conditions that support an incredible diversity of life. We tend to think of Earth as normal, as the default setting for what a planet should be. But the more we learn about the planets orbiting other stars, the more we realize that Earth is not normal at all. Earth is the anomaly. Earth is the weird one. Out of the thousands of exoplanets we have discovered, none of them are exactly like Earth. Some are close in terms of size or distance from their star, but none of them are perfect matches. And the vast majority of exoplanets we have found are nothing like Earth at all. They are super-Earths and mini-Neptunes and hot Jupiters and ultra-short-period lava worlds. They have atmospheres of helium and soot. They rain iron and diamonds. They orbit dead stars and get their atmospheres ripped away by radiation. In the gallery of planets that the universe has created, Earth is not the standard model. Earth is the masterpiece, the exception, the one in a trillion planet, where everything lined up just right, the right distance from the right kind of star, the right mix of elements in the right proportions, the right amount of water, the right kind of atmosphere, the right magnetic field to protect that atmosphere from solar wind, the right tectonic activity to recycle carbon and regulate the climate. Everything had to be exactly right, and it was. When you look at worlds like PSR, with its diamond rain and lemon shape and dead star host, you start to appreciate just how remarkable our own world truly is. Every one of those extreme exoplanets is a reminder of how easily things could have gone differently, how easily the dice of cosmic formation could have rolled a different way and produced a hell world instead of a garden world. That perspective is one of the most valuable things the James Webb Space Telescope is giving us. Not just knowledge about distant planets, but a deeper appreciation for our own. Every time Webb discovers a new nightmare world, it is also telling us something important about how precious and improbable our own existence is. And that leads to another profound question. If Earth is truly exceptional, what does that mean for the search for life in the universe? The discovery of these extreme exoplanets does not necessarily make it more or less likely that life exists elsewhere, but it does change the conversation. It tells us that the universe is far more diverse and far more extreme than we previously imagined. It tells us that the conditions for life, at least life as we know it, are probably rarer than we thought. The universe is clearly capable of producing an astonishing variety of worlds, but most of those worlds are hostile beyond anything we can survive. At the same time, these discoveries also tell us that nature is full of surprises. If a planet can exist with an atmosphere of pure carbon soot, orbiting a dead star, defying every known formation mechanism, then maybe the conditions for life can arise in ways we have not imagined either. Maybe there are forms of life out there that are as alien to us as PSR is to our own solar system. Life that thrives in environments we would consider impossible. Life that uses chemical processes we have never encountered. Life that is as far removed from anything on Earth as a diamond lemon planet is from a blue marble in space. That is the beauty of the unknown. Every time we discover something that breaks our models, it also opens a door to possibilities we had not considered. The universe is not just bigger than we thought. It is stranger than we thought. And in that strangeness, there might be room for wonders we cannot even imagine yet. Now let me bring us back to the James Webb Space Telescope itself, because the instrument at the center of all these discoveries deserves some attention. Webb is not just any telescope. It is the most powerful, most expensive, and most ambitious space telescope ever built. And understanding how it works helps us appreciate why it is able to find things that no other telescope ever could. The heart of Webb is its primary mirror. It is made of 18 hexagonal segments, each one coated in a thin layer of gold. Together, they form a mirror that is 6.5 meters across. That is more than 2.5 times wider than the Hubble Space Telescope's mirror. And because the amount of light a telescope can collect scales with the area of its mirror, Webb can gather more than 6 times as much light as Hubble. That means it can see fainter objects farther away, in more detail than any telescope before it. But the mirror is only part of what makes Webb special. The other key feature is its sunshield. Webb observes the universe in infrared light. Infrared is the kind of light that warm objects emit. Your body emits infrared light. The walls of your room emit infrared light. And therein lies the problem. If the telescope itself is warm, it will glow in the very wavelengths it is trying to observe. It would be like trying to take a photograph in a room filled with fog. The telescope's own heat would drown out the faint signals from distant planets and stars. To solve this problem, Webb has a sunshield the size of a tennis court. It is made of 5 layers of a special material called kapton, and it blocks light and heat from the sun, the earth, and the moon. The sunshield keeps Webb's instruments at a temperature of about -233 degrees Celsius. That is -387 degrees Fahrenheit. Just 40 degrees above absolute zero, the coldest temperature possible. At that temperature, Webb's instruments are cold enough to detect the faintest infrared whispers from the most distant corners of the universe. And Webb does not orbit the Earth like Hubble does. It sits at a point in space called the second Lagrange point, or L2, about 1 million miles from Earth. At that distance, the Earth and the Sun are always on the same side of the telescope, which means the sunshield can block both of them simultaneously. This gives Webb a permanently cold, dark, stable viewing environment, perfect for studying the faint infrared glow of planets orbiting distant stars. It was exactly this combination of features, the massive mirror, the ultra-cold instruments, and the stable viewing position, that made the discovery of PSR's atmosphere possible. Michael Zhang, the lead researcher, explained this directly. He said that on the Earth, lots of things are hot, and that heat really interferes with the observations because it is another source of photons that you have to deal with. He said it is absolutely not feasible from the ground. Only Webb, from its perch 1,000,000 miles away from Earth, with its instruments chilled to near absolute zero, could have detected the carbon soot and diamond-forming atmosphere of this impossible planet. That is a sobering thought. This planet has been out there, orbiting its dead star, raining diamonds for billions of years. And until we built this one specific telescope and pointed it in exactly the right direction, we had no idea it existed. We had no idea that such a planet could exist. What else is out there right now, at this very moment, that we simply do not have the tools to see yet? That is the question that keeps astronomers up at night. That is the question that drives the push for bigger, better, more powerful telescopes. Because every time we build a new instrument that can see a little farther or a little more clearly, we find things that blow our minds, things we never expected, things that change everything. And the James Webb Space Telescope is just getting started. It was designed to operate for at least 10 years, and it has enough fuel to potentially last 20 years or more. That means we have decades of discoveries ahead of us. Decades of looking deeper into the universe. Decades of finding more impossible planets, more unexplainable atmospheres, more phenomena that force us to rewrite the textbooks. But right now, let us stay focused on the disturbing discoveries we already have. Because I want to dig even deeper into what makes the diamond planet's atmosphere so fundamentally wrong, according to our understanding of chemistry. Think about the periodic table of elements. You probably remember it from school. Rows and columns of elements, organized by their properties. Hydrogen at the top, helium next to it, then lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on. In the universe at large, the most abundant elements are hydrogen and helium. They make up roughly 98% of all normal matter. The next most abundant elements are oxygen, carbon, neon, and nitrogen, then iron, silicon, magnesium, and sulfur. These elements, created in the furnaces of stars and spread across the cosmos by supernovae, make up the raw material from which planets are built. When a planet forms, it draws from this cosmic pantry. The exact mix depends on the conditions, the temperature, the pressure, the composition of the surrounding disk, and the details of the formation process. But in general, you expect to see a representative sample of the available elements. If the universe is 98% hydrogen and helium, then a gas giant planet should be mostly hydrogen and helium. If the surrounding material contains significant amounts of oxygen and carbon, then you expect to see molecules like water, methane, and carbon dioxide in the planet's atmosphere. This is exactly what we find on every other exoplanet we have studied. Hot Jupiters have atmospheres dominated by hydrogen, with traces of water, sodium, potassium, and sometimes more exotic molecules like titanium oxide or vanadium oxide. Even the weirdest hot Jupiters, planets like WASP 76b with its iron rain, or WASP 18b with its water-destroying temperatures, still have atmospheres that are fundamentally based on hydrogen and helium. They are extreme versions of the basic recipe, but they still follow the recipe. PSR does not follow the recipe. It threw the recipe away. Its atmosphere is dominated by helium and carbon, with virtually no hydrogen, no oxygen, and no nitrogen. That is like going to a bakery and finding a cake made entirely of flour and sugar, with no eggs, no butter, no milk, and no leavening agent. It should not hold together. It should not exist in that form. The ingredients are wrong for the product. The specific forms of carbon detected, C2 and C3, are particularly telling. C2 is 2 carbon atoms bonded together. C3 is 3 carbon atoms in a chain. These molecules are fragile in a sense. They are highly reactive with oxygen. If there were any significant amount of oxygen in the atmosphere, the carbon would quickly combine with the oxygen to form carbon monoxide or carbon dioxide. The fact that C2 and C3 can exist in detectable quantities means that the oxygen abundance must be vanishingly small, essentially zero. Same with nitrogen. Nitrogen reacts with carbon under certain conditions to form hydrogen cyanide and other molecules. If there was significant nitrogen present, the atmospheric chemistry would be completely different. The C2 and C3 signatures would be wiped out. So, their detection is not just evidence that carbon is present. It is evidence that oxygen and nitrogen are virtually absent, which, again, is something that has never been observed on any other planet. Now, some of you might be thinking, okay, but what about carbon planets? Have scientists not theorized about planets made primarily of carbon? And the answer is yes, they have. The idea of carbon planets has been floating around in theoretical astrophysics for years. These would be planets where, instead of the usual silicon and oxygen-based rocks we have on Earth, the geological structures would be made of carbon compounds, silicon carbide instead of silicate, diamond and graphite instead of quartz and feldspar. But even in these theoretical models, the planets still have other elements present. They still have some oxygen, some nitrogen, some hydrogen. The carbon is more abundant relative to the other elements, but it is not the only thing there. PSR goes beyond even the most extreme carbon planet models. It is not just carbon enriched. It is carbon dominated, with essentially nothing else except helium. That is a level of chemical purity that no natural process we know of can produce. Unless, of course, the process that created this planet is something we have not thought of yet. And that is exactly what the researchers are proposing. There must be some formation mechanism, some sequence of events that can produce a planet-sized object with a pure helium and carbon atmosphere. We just do not know what it is. The discovery is not an endpoint. It is a starting point, a challenge to the entire field of planetary science to come up with new ideas, new models, new theories that can account for what Webb has observed. That is how science is supposed to work. You observe something unexpected. You try to explain it with existing theories. If the existing theories fail, you develop new ones. The new theories make new predictions. You test those predictions with new observations, and the cycle continues, pushing our understanding forward one step at a time. PSR is currently at the first step. The observation, the shock, the what the heck is this moment, the explanation will come later. But right now, the not knowing is part of what makes this so fascinating and so disturbing. Let me shift gears now and talk about something that connects all of these disturbing exoplanet discoveries together. A theme that runs through every one of them. That theme is the concept of extremes. Every one of these planets exists at the edge of what we thought was possible. They push every parameter to its limit. Temperature, gravity, radiation, chemical composition, orbital dynamics. In every case, the planet takes one or more of these parameters and cranks it up to a level that breaks our models. And that raises an interesting philosophical question. Is there a limit to how extreme a planet can be? Is there some point beyond which the laws of physics simply will not allow a planet to exist? Or is the universe capable of producing worlds that are even more extreme than the ones we have found so far? Based on what we know about physics, there are some hard limits. A planet cannot be more massive than about 13 times the mass of Jupiter without becoming a brown dwarf, a type of failed star that is too massive to be called a planet. A planet cannot orbit too close to its star without being torn apart by tidal forces. The exact distance depends on the masses involved, but there is a hard line called the Roche limit, beyond which the gravitational forces would rip the planet to shreds. But within those hard limits, there is an enormous range of possibilities, and we keep finding planets that explore more and more of that range. Planets closer to their stars than we thought possible. Planets with more extreme temperatures than we thought possible. Planets with more unusual atmospheres than we thought possible. Every time we think we have found the edge of the possible, some planet comes along and pushes the boundary further. PSR might represent the current extreme in terms of atmospheric composition. TOI 561b represents an extreme in terms of atmospheric resilience, maintaining an atmosphere against all odds. WASP 76b represents an extreme in terms of atmospheric chemistry, with its iron rain. WASP 121b represents an extreme in terms of atmospheric loss, with its twin helium tails. And WASP 18b represents an extreme in terms of temperature mapping, with regions hot enough to destroy water at the molecular level. Each one pushes a different boundary. Each one tells us something new about the range of planetary possibilities. And together, they paint a picture of a universe that is far more creative, far more diverse, and far more extreme than we ever imagined. Let me tell you about one more phenomenon that makes these discoveries even more remarkable. It is called atmospheric escape, and it is one of the most dramatic processes that can happen to a planet. Atmospheric escape is exactly what it sounds like. It is the process by which a planet loses its atmosphere to space. And on extreme exoplanets, it can happen at breathtaking scales. On Earth, atmospheric escape happens too, but at a very slow rate. Hydrogen is light enough that some of it gradually drifts away from the top of our atmosphere and escapes into space. But Earth's gravity is strong enough and our atmosphere is thick enough that this process is negligible. We are not in danger of losing our air anytime soon. But on extreme exoplanets, atmospheric escape can be violent and rapid. When a planet orbits very close to its star, the intense radiation heats the upper atmosphere to extreme temperatures. The gas molecules gain so much energy that they can exceed the planet's escape velocity and fly off into space. In the most extreme cases, the atmosphere literally boils away. It streams off the planet in a continuous flow, like steam rising from a pot of boiling water. This is what is happening to WASP 121b, the planet with the twin helium tails. The radiation from its star is heating the upper atmosphere so much that helium atoms are being blasted off into space. And they are not just drifting away quietly. They are streaming away in two distinct tails that span more than half the planet's orbit. The leading tail is pulled forward by the star's gravity. The trailing tail is pushed backward by the star's radiation pressure. Together, they create a haunting image of a planet being slowly disassembled by its own star. And here is the sobering part. If this process continues, and there is no reason to think it will not, WASP 121b will eventually lose a significant portion of its atmosphere. Over billions of years, the planet could be stripped down from a hot Jupiter to something much smaller. Maybe a dense core of heavy elements, maybe something even weirder. The planet as it exists today is a snapshot in time, a moment in a long, slow process of destruction. This connects back to our diamond planet in a fascinating way. Remember, PSR is classified as part of a black widow system, where the pulsar is slowly consuming its companion. The companion that we now call a planet might have once been much larger. It might have once had a much more extensive atmosphere. It might have been a completely different type of object billions of years ago. What we are seeing now is whatever remains after billions of years of the pulsar slowly stripping away material and bombarding the companion with radiation. If that is true, then the pure carbon atmosphere we see today might be the last remnant of a much more complex original composition. Everything else, the hydrogen, the oxygen, the nitrogen, might have been stripped away over eons, leaving behind only the heaviest and most stubborn components. Carbon, being relatively stable and forming strong molecular bonds, might have been the last thing standing after everything else was blown away. That is still speculative, of course. The researchers are not claiming to know the full history of this system. But it is a thought-provoking possibility. A planet that has been slowly stripped down to its bare essentials over billions of years, until all that remains is an atmosphere of helium and carbon soot, raining diamonds in the glow of a dead spinning star. If that is what happened, then this planet is not just strange. It is a ruin, the remnant of something that was once very different, transformed beyond recognition by the relentless forces of nature operating over unimaginable timescales. And that idea, the idea of cosmic ruins, is one of the most poignant concepts in all of astronomy. We are used to thinking of ruins in terms of human civilization, crumbling temples, fallen empires, ancient cities reclaimed by the jungle. But the universe creates ruins too. Dead stars, stripped planets, fading galaxies, the wreckage of systems that once blazed with energy and activity, but have been ground down by time and gravity and radiation into strange, haunting remnants of their former selves. PSR might be one of the most dramatic cosmic ruins ever found. A once vibrant system with a massive star and a stellar companion that has been transformed over billions of years into a spinning dead star and a lemon-shaped diamond planet. The last two dancers on an empty dance floor still moving through their orbits long after the music has stopped. That is the kind of image that stays with you. That is the kind of discovery that changes how you think about the universe. Not just because it is scientifically fascinating, although it certainly is, but because it tells a story of violence and transformation and endurance, a story that plays out across billions of years in conditions that make our own planet's history seem gentle by comparison. And it is all happening right now. This planet is out there right now, at this very moment, orbiting its pulsar once every 7.8 hours, raining diamonds, rotating its atmosphere backward, being lemon-shaped by the gravity of a dead star. It has been doing this for billions of years, and it will keep doing it for billions more, long after our sun has exhausted its fuel and Earth has been swallowed by the expanding red giant. Long after the last human being has taken their last breath. Long after our entire civilization has become nothing more than a thin layer of sediment in the geological record. That diamond planet will still be there, still orbiting, still raining, still impossible, still beautiful. Let us take a step back now and consider the broader implications of these discoveries for the future of space science. Because the James Webb Space Telescope is not operating in isolation. It is part of a larger ecosystem of astronomical instruments and missions that are working together to understand the universe. On the ground, observatories like the European Southern Observatory's Very Large Telescope in Chile and the Gemini Observatory in Hawaii are conducting complementary observations. These ground-based telescopes can study exoplanet atmospheres at high spectral resolution, identifying specific chemical elements and measuring atmospheric dynamics with incredible precision. The discovery of iron rain on WASP-76b, for example, was made using the espresso spectrograph on the VLT. These instruments cannot do everything that Webb can do, but they can do some things even better. In space, other missions are contributing their own pieces to the puzzle. The European Space Agency's JWST telescope, which detected hints of the glory effect on WASP-76b, is designed specifically to study known exoplanets in great detail. The Transiting Exoplanet Survey Satellite, or TESS, is scanning the entire sky for new exoplanets, adding hundreds of new candidates to the catalogue every year. Many of the planets that Webb is now studying in detail, including TOI 561b, were first discovered by TESS, and on the horizon, there are even more powerful instruments being developed. The European Space Agency's Ariel mission, scheduled for launch in the late 2020s, will be the first space telescope dedicated entirely to studying exoplanet atmospheres. It will observe roughly 1,000 exoplanets over its mission lifetime, building a comprehensive catalogue of atmospheric compositions across a wide range of planet types. NASA's Nancy Grace Roman Space Telescope, also planned for launch soon, will have the ability to directly image exoplanets using a coronagraph, a device that blocks out the light of the host star to reveal the much fainter planet beside it. Together, these instruments will give us a far more complete picture of the exoplanet population than we have today. We will be able to study not just individual remarkable planets, but the statistical patterns across hundreds and thousands of worlds. How common are carbon-dominated atmospheres? How many planets maintain atmospheres despite being too close to their stars? How many worlds rain exotic materials from their skies? These questions can only be answered with large surveys, and the tools to conduct those surveys are either already operational or just around the corner. And that brings me to perhaps the most exciting prospect of all: the possibility that somewhere out there, among the trillions of planets in the universe, there might be one that is even more disturbing than PSR, even more extreme than anything we have found so far, even more impossible to explain with our current understanding of physics. Because if there is one thing we have learned from the James Webb Space Telescope, it is that the universe always has another surprise up its sleeve. Every time we think we have seen the strangest possible planet, something stranger shows up. Every time we think we have pushed the boundaries of the possible, some distant world pushes them further. The universe is not done shocking us, not by a long shot. So let me ask you a question. What would it be like to actually visit one of these disturbing planets? I know it is impossible with our current technology. The nearest of these worlds is hundreds of light years away, and we do not have the ability to travel even to the nearest star, which is only about 4 light years from Earth. But as a thought experiment, imagining what it would be like to experience these worlds firsthand can give us an even deeper appreciation for just how alien they truly are. Let us start with the Diamond Planet. Imagine you are in a spacecraft, approaching PSR. The first thing you would notice is the pulsar itself. Or rather, you would not notice it visually, because the pulsar is tiny, only about 12 miles across, far too small to see at any distance. But your instruments would be screaming. They would be detecting intense bursts of radio waves, arriving 300 times per second with clockwork precision. And they would be detecting a flood of gamma radiation, high-energy photons that would be lethal to any unshielded human being. You would need heavy shielding just to survive in this neighborhood. As you got closer to the planet, you would start to see it. A dark, looming sphere, slightly elongated, glowing faintly in infrared. Not the warm, inviting blue of Earth, not the swirling white and tan of Jupiter, This would be a world shrouded in dark carbon clouds, lit from within by the heat of its own tortured existence. The color would be somewhere between deep red and orange, the glow of a world heated to nearly 2,000 degrees Celsius. Getting closer still, you would see the clouds, thick, dark, roiling masses of pure carbon soot. Imagine the blackest storm clouds you have ever seen on Earth, and then multiply the darkness by 100. These clouds would absorb almost all visible light, making them appear as deep, impenetrable darkness against the already dim glow of the planet. And somewhere within those clouds, deep below the visible surface, diamonds would be forming, condensing out of the carbon-rich atmosphere like snowflakes forming in a winter storm, except instead of ice crystals, you would get diamond crystals, falling deeper and deeper into the planet's interior. The wind would be the next thing to notice. The entire atmosphere of this planet is racing around in the opposite direction of the planet's rotation. Imagine standing on the surface, if there were a surface to stand on, and looking up at a sky that is rushing past you at tremendous speed, going the wrong way, like being on a merry-go-round while the roof above you spins in the other direction. The disorientation would be profound. And then there is the gravity. The planet has roughly the mass of Jupiter, but it is stretched into a lemon shape by the tidal forces of the pulsar. If you were standing at the equator, you would feel the tug of the planet's gravity pulling you down, but also the tidal force of the pulsar pulling you sideways toward the dead star. The gravitational environment would be complex, constantly shifting as the planet whipped around its orbit every 7.8 hours. Speaking of the orbit, think about how fast things would be moving. The planet is only 1 million miles from the pulsar. It completes a full orbit in less than 8 hours. That means it is moving through space at an incredible velocity. The sunrise, if you could call it that, since the pulsar does not emit much visible light, would come and go faster than you could blink in cosmic terms. Day and night would cycle through in hours, and because the planet is tidally locked, there would not really be a day and night cycle at all in the traditional sense. One side always faces the pulsar, absorbing its gamma radiation. The other side faces away, slightly cooler, but still brutally hot. You would not survive a visit to this planet, not even for a fraction of a second. The temperature alone would kill you instantly. The radiation would be lethal. The atmosphere is unbreathable. There is no solid surface to stand on. It is, in every meaningful sense, a world that is completely and utterly hostile to life as we know it. And yet, it is real. It exists. And there might be trillions of worlds just as extreme or even more extreme scattered across the universe. Now imagine visiting Towai 561b, the lava hell world. This would be a different kind of nightmare. Instead of a dark, sooty carbon atmosphere, you would be looking at a world of fire. The day side, the side that permanently faces the star, would be an ocean of molten rock stretching from horizon to horizon. The surface temperature of around 1800 degrees Celsius means that everything is liquid. The rocks, the minerals, everything that would be solid on Earth is flowing and churning, like water in a pot. Above the magma ocean, a thick atmosphere of volatile gases would shimmer and glow. Water vapor, perhaps. Silicate vapor, certainly. And clouds made not of water droplets, but of tiny particles of rock. Sand clouds floating high in the atmosphere, catching the light of the star and scattering it in ways that would be hauntingly beautiful if you could see it without being instantly incinerated. The winds on this planet would be intense. The temperature difference between the day side and the night side would drive powerful atmospheric circulation, with winds carrying heat from the burning day side to the frozen night side. On the night side, when no starlight reaches, the temperatures would drop. The magma might solidify into rock. The volatile gases might condense. The transition zone between the two hemispheres, the line between eternal day and eternal night, would be a region of extreme weather, violent storms, rapid temperature changes, constantly shifting conditions, and somewhere beneath the surface, the magma ocean would be engaged in its eternal exchange with the atmosphere. Gases bubbling up from the molten rock, escaping into the air. Other gases being pulled back down, dissolved back into the magma. A planet that breathes through its own molten surface. In and out. An endless cycle that has been going on for 10 billion years and shows no signs of stopping. Now picture WSP-76b. This one might be the most viscerally disturbing to imagine. You approach the planet and see a world divided in two. The day side facing the star is a blazing inferno. Temperatures above 2400 degrees Celsius. Hot enough to vaporize iron, the atmosphere on this side is filled with metallic vapors, swirling in superheated winds. If you could somehow see the day side, it would glow white hot, like the interior of a blast furnace. But the night side is different. As you cross the Terminator line, the boundary between day and night, the temperature drops dramatically. It is still insanely hot by human standards, still above 1500 degrees Celsius, but it is cool enough for a phase transition to occur. The iron vapor that fills the atmosphere on the day side begins to condense. Tiny droplets of liquid iron form in the air, and they start to fall. Imagine standing on the night side of this planet and looking up. The sky would be filled with a steady downpour of glowing iron droplets, red-hot liquid metal, falling from the clouds like rain. Each drop would be incandescent, glowing with heat as it fell through the superheated atmosphere. The sky would look like it was bleeding fire, a constant, unending rain of molten metal falling from dark clouds in a sky lit only by the ambient glow of the planet's own heat. The sound, if sound could propagate in such an environment, would be a constant hissing and sizzling, drops of liquid iron splattering through an atmosphere of vaporized rock and metal, a hellscape beyond anything Dante could have imagined, beyond anything any human storyteller has ever dreamed up. And it is real. It is happening right now, 640 light-years away, in the constellation Pisces. These thought experiments are not just fun exercises in imagination. They serve a scientific purpose too. By imagining what it would be like to visit these worlds, we engage with the science on a deeper level. We move beyond the numbers and the data and start to feel the reality of what these discoveries mean. A temperature of 2400 degrees Celsius is just a number. But imagining iron rain falling from a burning sky makes it real. An atmospheric composition of helium and carbon is just a chemical analysis. But imagining dark soot clouds raining diamonds makes it vivid. And that vividness matters, because the more real these discoveries feel, the more we appreciate the incredible work that scientists are doing and the incredible universe we live in. These are not abstract academic exercises. These are real places, real worlds, real phenomena happening right now in real parts of the real universe. And the fact that we can study them from 1,000,000 miles away using a telescope that can detect the faint infrared glow of a planet orbiting a dead star is one of the most remarkable achievements of human civilization. Now, Let me bring this whole conversation to a point, because I have taken you on a long journey through some of the most extreme and disturbing worlds the James Webb Space Telescope has ever found. We have talked about diamond lemon planets, lava hell worlds, iron rain, twin helium tails, and three-dimensional temperature maps of alien atmospheres. We have explored the science, the history, and the implications of these discoveries. We have imagined what it would be like to visit these impossible worlds, and we have grappled with the profound questions they raise about our understanding of the universe. So what does it all come down to? What is the takeaway? Here is what I think. The most disturbing thing about these planets is not their extreme temperatures. It is not their bizarre atmospheres. It is not their impossible formation stories. The most disturbing thing is what they reveal about the limits of our knowledge. We live in an age where information is everywhere. We can look up almost anything on our phones in seconds. We have access to the accumulated knowledge of all of human history, and that can create an illusion that we have figured most things out, that the big questions are mostly answered, that science is just filling in the details of a picture that is already well understood. These discoveries shatter that illusion. They remind us that the universe is vaster, stranger, and more mysterious than we can comprehend. That our theories, as powerful as they are, only capture a tiny fraction of the truth, that there are entire categories of objects and phenomena out there that we have not even begun to imagine, let alone understand. And that is not scary. That is inspiring. It means the age of discovery is not over. It means there are still frontiers to explore, questions to answer, and surprises to find. It means that the next generation of scientists, the kids watching videos like this right now, have the opportunity to make discoveries that will be just as groundbreaking and just as mind-blowing as anything the James Webb Space Telescope has found. Every great discovery in science started with a moment of confusion, a moment when the data did not match the theory, a moment when a scientist looked at their results and said, "What the heck is this?" That moment of confusion is not a failure. It is a gift. It is nature telling us that there is something new to learn, something we missed, something waiting to be understood. PSR is one of those gifts, a planet that should not exist, wrapped in an atmosphere that defies explanation, raining diamonds in the shadow of a dead star. It is nature saying, "You think you understand how planets work? Think again. You think you have figured out the rules? I have a lemon-shaped exception for you." And here is the beautiful part. The scientists who discovered this planet are not discouraged by the mystery. They are energized by it. Michael Zhang, Peter Gao, Maya Belesne, Roger Romani, and the entire team behind this discovery are not throwing up their hands and giving up. They are rolling up their sleeves and diving deeper. They are developing new models, testing new theories, planning new observations, working to crack the mystery of how this impossible planet came to be. That is what science does. It does not run from the unknown. It runs toward it. It takes the confusion and turns it into curiosity. It takes the impossible and tries to make it possible to understand. And in doing so, it pushes the boundaries of human knowledge forward, one discovery at a time. The James Webb Space Telescope is the most powerful tool we have ever built for this purpose. It has already shown us things we never thought possible, planets we never imagined, atmospheres we never predicted, and it is just getting warmed up. In the years and decades ahead, it will continue to surprise us, continue to challenge us, continue to show us that the universe is far stranger and far more wonderful than anything we could have dreamed. So the next time you look up at the night sky, Take a moment to think about what is really out there, beyond the familiar stars and constellations, beyond the comforting glow of the moon, out there in the darkness, 750 light years away, there is a lemon-shaped planet raining diamonds, a world born from the death of a star with an atmosphere of soot and helium, orbiting a dead lighthouse that spins 300 times a second. It is real, it is there, and it is just one of the trillions of worlds scattered across the cosmos, each one with its own story, its own mysteries, and its own capacity to blow our tiny human minds. That, to me, is the most beautiful thing about the universe. Not that we understand it, but that it keeps reminding us how much we still have left to learn. And with tools like the James Webb Space Telescope, we have never been better equipped to learn it. Let me leave you with one final thought about the diamond planet and what it represents. In many ways, this planet is a mirror, not a literal mirror, obviously, but a metaphorical one. When we look at PSR and find ourselves confused, awed, and disturbed, we are actually learning something about ourselves. We are learning about the edges of our own understanding. We are discovering where our knowledge ends and our ignorance begins. And that is not a comfortable feeling. Nobody likes to feel ignorant. Nobody likes to be reminded of the things they do not know. But that discomfort is the engine of discovery. It is the fuel that drives science forward. Every scientist who has ever made a great breakthrough started from a place of not knowing, not understanding, being confused by something that did not fit the existing models. Isaac Newton did not understand why the apple fell from the tree. That confusion led to the theory of gravity. Albert Einstein did not understand why the speed of light was always the same. That confusion led to the theory of relativity. Edwin Hubble did not understand why distant galaxies were moving away from us. That confusion led to the discovery of the expanding universe. And now, Michael Jang and his colleagues do not understand how a lemon-shaped diamond planet can exist around a dead star. That confusion will lead somewhere too. We just do not know where yet. But wherever it leads, it will be worth following, because the story of science is the story of humanity at its best. Curious, persistent, humble, and brave. Willing to face the unknown and find beauty in the confusion. Willing to admit what we do not know and work tirelessly to figure it out. That is who we are at our core. That is what makes us remarkable as a species. And that is why discovering a disturbing, impossible, diamond-raining lemon planet, orbiting a dead star 750 light-years away, is not just a scientific achievement. It is a triumph of the human spirit. The James Webb Space Telescope has given us a window into the most extreme corners of the cosmos. And every time we look through that window, we see something that changes us, something that challenges us, something that reminds us that the universe is infinite in its complexity and that our journey to understand it has barely begun. So keep looking up, keep asking questions, keep being curious, because the universe has secrets to share with anyone who is willing to listen. And the most disturbing planet in the known universe might just be the most important one we have ever found. But before I wrap things up, I want to explore one more dimension of this story that I think is often overlooked, the human dimension. Because behind every one of these incredible discoveries, there are real people, real scientists who have dedicated their lives to understanding the universe. And their stories are just as inspiring as the planets they study. Take Michael Jang, for example. He is the principal investigator on the PSR study. A postdoctoral fellow in exoplanet atmospheres at the University of Chicago. He has spent years developing the techniques and expertise needed to analyze the spectra of distant worlds. He probably spent countless late nights staring at computer screens, writing code, running simulations, and analyzing data. And when the spectrum of this impossible planet finally appeared on his screen, all of that work paid off in a moment of pure, unscripted wonder. Or consider Maya Belesne, the graduate student at Stanford, who modeled the planet's shape and orbital geometry. She is at the very beginning of her scientific career. Imagine being a graduate student and contributing to a discovery that literally rewrites the rules of planetary science. That is the kind of experience that shapes a career, the kind of moment that a scientist remembers for the rest of their life. These are the people behind the discovery. And there are many more. Co-authors on the paper, telescope operators who pointed Webb at the right coordinates, engineers who built and maintained the instruments that made the observation possible, software developers who wrote the code to process the raw data. Each one of them played a role in this discovery. Science is a team sport, and the team behind PSR is world-class, and that team is not done. They are already planning follow-up observations. They want to study the planet at different wavelengths to learn more about the deeper layers of its atmosphere. They want to track how the atmosphere changes over time. They want to compare this planet to other Black Widow system companions to see if the pure carbon atmosphere is unique to this world, or if it might be a common feature of these extreme systems. Those follow-up observations could take years. Science moves slowly, especially when you are trying to get time on the most in-demand telescope in the world. Webb's observation schedule is packed with thousands of proposed projects, each one competing for precious hours of telescope time. Getting approved for a new round of observations requires a compelling scientific case and a lot of patience. But the team behind this discovery has both, and the scientific case for studying this planet further is about as compelling as it gets. In the meantime, theorists around the world are already working on new models that might explain PSR's impossible atmosphere. Papers are being written, simulations are being run, conference presentations are being planned. The scientific community moves fast when a discovery this significant comes along. Within a year or two, we may see several competing theories proposed, each offering a different explanation for how this planet came to be. Some of those theories will be tested against the data and found wanting. Others might survive, and eventually, one of them might emerge as the leading explanation. But that process takes time, and in the meantime, the mystery remains, which is exactly the kind of situation that makes science so compelling. We are living in the gap between the question and the answer, the space between the observation and the explanation. And that gap is where the magic happens. That is, where imaginations run wild and new ideas are born. Let me talk about something else that makes the Diamond Planet discovery even more remarkable. It is the fact that this planet was hiding in plain sight for years. Remember, the companion was first detected in 2017 using radio telescopes. For 6 years, from 2017 to 2023, we knew something was orbiting that pulsar. We knew its approximate mass. We knew its orbital period, but we could not see it. We could not study its atmosphere. We could not determine what it was made of. That 6-year gap between detection and characterization is a powerful reminder of how much depends on having the right tool for the job. Radio telescopes could detect the planet's gravitational influence on the pulsar, but they could not directly observe the planet itself. Ground-based optical and infrared telescopes could not study it either, because the thermal radiation from the Earth's own atmosphere would have drowned out the faint infrared signal from the planet. It took a space telescope, operating at near absolute zero temperatures, 1,000,000 miles from Earth, to finally reveal the true nature of this world. How many other planets are out there right now, detected but not yet characterized? How many companions to pulsars and other exotic stars are sitting in our catalogues, waiting for their turn with Webb or some future telescope? The answer is probably hundreds, if not thousands. Each one of them could be hiding an atmosphere just as surprising as PSRs. Each one of them could be the next "what the heck is this" moment. That thought is both thrilling and humbling. We have catalogues full of exoplanets that we know almost nothing about beyond their mass and orbit. They are entries in a database, numbers on a spreadsheet. But each one is a real world, with real physical properties, real atmospheric chemistry, and real stories to tell. And we will not know those stories until we look more closely. The James Webb Space Telescope has the ability to characterize hundreds of exoplanet atmospheres over its remaining lifetime. Each observation takes hours or days of telescope time. Each one produces a spectrum that can be analyzed for chemical signatures, and each one has the potential to reveal something completely new and unexpected. The rate of discovery is only going to accelerate from here. And beyond Webb, the next generation of ground-based telescopes is coming online. The extremely large telescope, being built by the European Southern Observatory in Chile, will have a primary mirror 39 meters across. That is 6 times wider than Webb's mirror. It will be able to study exoplanet atmospheres from the ground with unprecedented resolution. The giant Magellan telescope, also under construction in Chile, will have 7 mirror segments that work together to create the equivalent of a 25-meter mirror. And the 30-meter telescope, planned for construction in Hawaii, will provide another powerful ground-based platform for exoplanet science. Together with Webb and the fleet of space-based observatories, these ground-based giants will give astronomers an unprecedented toolkit for studying the planets that orbit other stars. We are entering a golden age of exoplanet science, a time when the pace of discovery will be faster than ever before, a time when the catalogue of characterized exoplanet atmospheres will grow from dozens to hundreds to thousands, and with each new entry in that catalogue, we will learn something new about the incredible diversity of worlds that the universe has created. Let me also take a moment to appreciate the sheer technical achievement of what Webb accomplished with this observation. Detecting the atmospheric spectrum of a planet 750 light-years away is like trying to read a license plate on a car that is parked in another city, while the car is in a dark garage, and the license plate is written in a language you have never seen before. The fact that we can do this at all is a testament to human ingenuity. The fact that we can do it well enough to identify specific molecules in an alien atmosphere is nothing short of miraculous. Every photon that arrived at Webb's detectors from this planet had been traveling through space for 750 years. Those photons left the planet around the year 1275, during the medieval period on Earth. Marco Polo was traveling the Silk Road. The Mongol Empire was at its height. The Notre Dame Cathedral was being built in Paris. And while all of that was happening on Earth, photons were streaming away from a lemon-shaped planet in the constellation Sculptor, carrying information about its carbon suit atmosphere in the specific wavelengths of light they carried. 750 years later, those photons arrived at the James Webb Space Telescope. They hit a gold-coated mirror. They were bounced to a secondary mirror. They were focused onto an infrared detector. They were converted into electrical signals. Those signals were transmitted by radio to a ground station on Earth. They were processed by computers. They were analyzed by scientists. And they told us something that nobody in the entire history of humanity had ever known before. That there is a planet out there with an atmosphere of pure carbon soot and diamonds. A planet that defies all known theories of formation. A planet shaped like a lemon by the gravity of a dead, spinning star. That chain of events, from photon to discovery, spanning 750 years and millions of miles, is one of the most remarkable achievements of human civilization. And it happened because generations of scientists, engineers, mathematicians, and dreamers built on each other's work, step by step, decade by decade, century by century, until we had the tools and the knowledge to reach across the cosmos and read the story written in starlight. That is the legacy of PSR. Not just a bizarre planet, not just a scientific puzzle, but a testament to what humanity can accomplish when it sets its mind to understanding the universe. A proof that our curiosity, our creativity, and our persistence can bridge the gap between our small blue world and the most extreme and distant corners of reality. And when you think about it that way, the discovery is not just disturbing, it is profoundly hopeful. Because if we can decode the atmosphere of an impossible planet 750 light years away, what else can we do? What other mysteries can we solve? What other frontiers can we reach? The answer is anything we set our minds to. The universe is vast, and our journey through it has just begun. Let me expand on something that deserves more attention. The idea of diamond rain. We have talked about it in the context of PSR, but it is actually a concept that scientists have been thinking about for a long time, even before this discovery. The idea first gained traction decades ago when planetary scientists began modeling the deep interiors of Jupiter, Saturn, Uranus, and Neptune. These giant planets in our own solar system have enormous pressure in their interiors, and they contain significant amounts of carbon, mostly in the form of methane. As you go deeper into the atmosphere of a gas giant like Jupiter or Saturn, the pressure increases rapidly. At certain depths, the pressures become so extreme that the carbon atoms in methane can be squeezed out of their molecular bonds and forced into new crystal structures. Specifically, they can be compressed into diamond. Laboratory experiments have confirmed that this is physically possible. Scientists have used high-powered lasers to simulate the extreme pressures found deep inside gas giants, and they have successfully created tiny diamonds in the process. On Neptune and Uranus, which are classified as ice giants rather than gas giants, the conditions for diamond formation may be even more favorable. These planets have higher concentrations of carbon-rich molecules relative to their hydrogen content, and the pressure-temperature profiles in their interiors pass through the diamond-forming sweet spot at accessible depths. Some researchers have estimated that diamond rain could be falling through the interiors of Neptune and Uranus right now, with the diamonds potentially accumulating around the planet's cores over billions of years. But what makes PSR different from all of these solar system examples is the sheer concentration of carbon in its atmosphere. On Jupiter and Saturn, carbon is a minor constituent. It exists as methane, which makes up less than 1% of the atmosphere. The diamond formation, if it occurs at all, happens deep in the interior, far below the visible cloud layers. On PSR, carbon is one of the dominant components of the atmosphere. It is not hiding deep inside the planet. It is right there, on the surface, forming clouds of soot that you could theoretically observe from space. The diamond formation is not happening at some inaccessible depth. It is happening in the atmosphere itself, as the soot clouds get compressed at relatively shallow depths compared to the gas giants in our solar system. That is a fundamentally different scenario. On Jupiter, diamond rain is a theoretical possibility that happens in a region we cannot directly observe. On PSR, diamond formation is an atmospheric process that we can study spectroscopically with the James Webb Space Telescope. We can actually see the carbon that will become diamonds. We can measure its abundance. We can track how it behaves at different points in the planet's orbit. For the first time in history, we have a world where diamond formation is not just a theory, but an observable phenomenon. And that opens up incredible possibilities for future research. If we can study the diamond-forming process on PSR in detail, we might learn things about carbon chemistry under extreme conditions that have applications far beyond astronomy. Understanding how carbon behaves under extreme pressure and temperature is relevant to materials science, to geology, to the study of the Earth's deep interior, and even to industrial diamond production. The universe is essentially running a diamond-forming experiment for us, at a scale that no laboratory on Earth could ever replicate. All we have to do is watch and learn. There is another aspect of PSR that I want to explore more deeply, because I think it gets to the heart of why this planet is so disturbing. It is the question of identity. What is this object really? We call it a planet because its mass falls in the planetary range and because the International Astronomical Union has classified it as such. But the more we learn about it, the less it resembles anything we traditionally associate with the word planet. Planets, in our understanding, are objects that formed from the leftover material around a young star. They condensed out of a disk of gas and dust, gradually growing larger through collisions and gravitational accumulation. They orbit main sequence stars, stars that are actively burning hydrogen fuel and producing light and heat. They have atmospheres that reflect the composition of the disk they formed from, with hydrogen and helium as the dominant gases and various trace molecules adding complexity. PSR checks almost none of these boxes. It does not orbit a main sequence star. It orbits a dead star, a neutron star that exhausted its fuel billions of years ago and collapsed into an ultra-dense remnant. It did not form from a disk of gas and dust around a young star. It either formed through some unknown process, or it started as something else entirely, perhaps a low-mass star, and was transformed into its current state by the pulsar's relentless radiation. Its atmosphere does not reflect the composition of any known star-forming region. It is dominated by carbon and helium, with an almost complete absence of the hydrogen, oxygen, and nitrogen that define every other planetary atmosphere we have studied. So is it really a planet? Or is it something new, something that does not have a name yet? The line between planets and stars has always been somewhat fuzzy. Brown dwarfs occupy a grey zone between the two categories. Sub-brown dwarfs and rogue planets blur the boundaries further. And now PSR introduces yet another category, ambiguity. A planetary mass object with a stellar origin, an unprecedented atmospheric composition, and a home address in one of the most extreme environments in the galaxy. Some scientists might argue that it does not matter what we call it. The physics is the same regardless of the label, and that is true to an extent. But categories matter in science because they help us organize our knowledge and identify patterns. When we say something is a planet, we are making an implicit claim about its formation history, its composition, and its relationship to its host star. When an object does not fit those implicit claims, it forces us to either expand our definition of what a planet can be or create a new category altogether. Either way, PSR is pushing us to think more carefully about the boundaries we draw around our cosmic neighbors. And that kind of boundary pushing is always productive, even if it is uncomfortable. Let me talk about one more fascinating detail that came out of the research: the way the researchers were able to determine the lemon shape of PSR. You might wonder how scientists can figure out the shape of a planet that is 750 light-years away and far too small to resolve as anything more than a point of light. The answer lies in the way the planet's brightness changes over the course of its orbit, because PSR is tidally locked to its pulsar, with one side always facing the star and the other always facing away. The amount of infrared light we see from the planet changes as it orbits. When the hot, star-facing side is pointed toward us, the planet appears brighter. When the cooler, far side is pointed toward us, it appears dimmer. By carefully tracking these brightness variations over a complete orbit, the researchers could build a model of how the heat is distributed across the planet's surface. But the brightness variations also contain information about the planet's shape. If the planet were a perfect sphere, the brightness changes would follow a specific mathematical pattern. If the planet is elongated, stretched into a lemon shape by tidal forces, the pattern changes. The researchers found that the observed brightness variations could only be explained if the planet was significantly non-spherical, with an equatorial diameter about 38% wider than its polar diameter. That is an extraordinary measurement. From 750 light-years away, using nothing but the subtle flickering of infrared light, scientists were able to determine that this planet is shaped like a lemon. That is the power of modern astrophysics. That is what happens when you combine a world-class telescope with world-class scientists and world-class analytical techniques. And it raises one more thought-provoking point. If we can determine the shape of a planet from its brightness variations, what else might those variations tell us? Could we detect weather patterns, volcanic eruptions, changes in atmospheric composition over time? The answer to all of these questions is potentially yes. As our instruments get more sensitive and our analytical techniques get more sophisticated, we will be able to extract more and more information from the faint light of distant worlds. Every photon carries a story, and we are getting better and better at reading those stories. The universe is a library, and the James Webb Space Telescope is teaching us how to read. Now, let me tell you about one more connection that ties this entire story together in a way that I find deeply moving. It is the connection between destruction and creation, between endings and beginnings. Because the story of PSR is ultimately a story about transformation, about how the universe takes something familiar and turns it into something entirely new. Think about the sequence of events that led to this planet's existence. It started with a massive star, probably 10 or 20 times the mass of our Sun. That star burned for millions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, building up layer after layer of increasingly complex atoms in its core. Then it ran out of fuel, and it died. Not quietly, not peacefully. It died in the most violent way possible, in a supernova explosion that briefly outshone an entire galaxy. But that death was not the end. It was a transformation. The core of the star collapsed and became a neutron star, a pulsar, a spinning beacon of radiation, dense beyond comprehension, only 12 miles wide, but carrying the mass of the Sun. The supernova explosion scattered the outer layers of the star into space, seeding the cosmos with the heavy elements that had been forged in the star's core. Elements like carbon, oxygen, nitrogen, and iron. the raw materials for future planets and future life. And then, over billions of years, the pulsar's relationship with its companion transformed that companion too. Whatever the companion started as, it was gradually stripped, bombarded, and reshaped by the pulsar's radiation and gravity. Its outer layers were blown away. Its composition changed. Its shape was distorted, until what remained was this strange, lemon-shaped, carbon-dominated world that we see today. Every step in that sequence was an act of destruction that led to an act of creation. The death of the star created the pulsar. The stripping of the companion created the planet. The pressure of the atmosphere creates diamonds. Destruction and creation intertwined, over and over again, at every scale. And that is not unique to this system. That is how the universe works everywhere. Stars die and seed the cosmos with heavy elements. Those elements form new stars and new planets. Planets collide and merge, creating new worlds from the wreckage of old ones. Even on Earth, the extinction of the dinosaurs, a catastrophic act of destruction, opened the door for mammals to diversify and eventually gave rise to us. Destruction and creation are not opposites. They are dance partners. PSR is one of the most dramatic examples of this cosmic dance. A planet born from the death of a star, shaped by the violence of its environment, carrying an atmosphere that no theory predicted. It is a monument to the universe's ability to create something new from something old, something unexpected from something destroyed, something beautiful from something violent. And in that sense, even the most disturbing planet in the known universe carries a message of hope, because it tells us that the universe is never finished, never done, never out of surprises. No matter how much is destroyed, something new always rises from the ashes. That is the fundamental nature of the cosmos, and it is reflected in the story of a lemon-shaped diamond planet orbiting a dead star in the constellation Sculptor. That is the thought I want to leave you with as we move toward the end of this video. Not just the strangeness of PSR, not just the science or the technology or the mystery, but the deeper truth that this discovery reveals. The truth that the universe is endlessly creative, endlessly surprising, endlessly capable of producing wonders that defy our imagination, and that we, as human beings, are incredibly fortunate to be alive at a time when we can witness these wonders, when we can study them, when we can share them with each other. Every generation has its own frontier of discovery. For the explorers of the 15th century, it was the unknown continents across the ocean. For the physicists of the 20th century, it was the subatomic world and the structure of the atom. For us, right now, in this moment, the frontier is the cosmos itself, the planets orbiting distant stars, the galaxies at the edge of the observable universe, the mysteries that the James Webb Space Telescope is revealing day by day, observation by observation, photon by photon. We are the generation that will catalogue the atmospheres of alien worlds, that will search for signs of life beyond Earth, that will map the extreme conditions on planets that rain diamonds and iron and molten rock. That is our frontier. That is our adventure. And PSR is one of the first landmarks on the map. And let me tell you, the map is going to get a lot bigger, because every year, the James Webb Space Telescope adds new entries to the catalogue of characterized exoplanet atmospheres. Every year, new surveys discover thousands of additional exoplanet candidates waiting to be studied. Every year, our analytical tools get sharper, our models get more sophisticated, and our understanding deepens just a little bit more. Within the next decade, we will know the atmospheric compositions of hundreds of exoplanets. we will be able to compare and contrast their chemistry, looking for patterns and outliers. We will be able to answer questions that we can barely formulate today. Questions like, how common are carbon-dominated atmospheres? Are there other planets out there with diamond rain? How many worlds maintain atmospheres despite being in conditions that should make it impossible? And lurking somewhere in that growing catalogue, there might be a planet even more disturbing than PSR, even more extreme, even more impossible to explain. A planet that will make the scientists who discover it say something even more emphatic than what the heck is this? A planet that will once again rewrite the rules and push the boundaries of what we thought was possible. I cannot tell you what that planet will look like. I cannot predict what surprises are waiting for us out there. But I can tell you this with absolute certainty. They are out there. The universe has never failed to surprise us, and it is not going to start now. Now, before I go, I want to circle back to something I mentioned at the very beginning of this video. The fact that the scientists who discovered this planet said, "What the heck is this?" when they first saw the data. That reaction tells you everything you need to know about why this discovery matters. It is not a measured, careful, diplomatic response. It is raw, honest, unfiltered. It is the sound of scientists encountering something that genuinely shocked them. And in a field where people spend their entire careers studying the strange and the extreme, it takes something truly extraordinary to produce that kind of reaction. Peter Gao, the Carnegie scientist who described that moment, has spent years studying planetary atmospheres. He has seen data from dozens of exoplanets. He is familiar with the full range of atmospheric compositions that have been observed in the universe. And when he saw the spectrum of PSR, his reaction was not calm scientific curiosity. It was genuine shock. What the heck is this? That is not the reaction of someone who found something mildly unusual. That is the reaction of someone who found something that broke the rules. And that moment, that instant of shock and confusion, is precisely where the most exciting science happens. It is the moment before the breakthrough, the darkness before the dawn. Right now, PSR is an unsolved puzzle, a question mark hanging in the constellation Sculptor, 750 light-years away, but it will not stay unsolved forever. Somewhere, right now, a graduate student or a postdoctoral researcher or a seasoned professor is working on a new theory that might explain this impossible planet. They are running simulations, crunching numbers, testing hypotheses, and one day, maybe 1 year from now, maybe 10 years from now, someone will figure it out. They will crack the code. They will explain how a lemon-shaped diamond planet with a pure carbon atmosphere can form around a millisecond pulsar. And when that day comes, it will not diminish the wonder of the discovery. It will amplify it, because the explanation will reveal something new about the universe, something we did not know before, a new piece of the cosmic puzzle, clicking into place, and that new piece will undoubtedly raise even more questions, even more mysteries, even more opportunities to say, what the heck is this? That is the never-ending cycle of discovery, and it is the most magnificent thing about being alive in this era of science. We have the tools, we have the talent, we have the curiosity, and the universe has an infinite supply of mysteries. The match could not be more perfect. So here is my personal take on all of this. I think the discovery of PSR is not just the most disturbing exoplanet finding from the James Webb Space Telescope. I think it is one of the most important scientific discoveries of the decade, not because of what we know about this planet, but because of what it reveals about what we do not know. It is a signal from the universe saying, you are on the right track, but you have a long way to go. Keep building your telescopes, Keep asking your questions. Keep looking up. Because I have so much more to show you. And honestly, I cannot wait to see what comes next. That wraps up our journey through the most disturbing planet the James Webb Space Telescope has ever found. From diamond rain to lemon shapes to dead star companions, this has been one of the wildest rides through the cosmos we have ever taken on this channel. If you made it this far, you are a real one. And I appreciate you sticking with me through this deep dive into the strangest corner of the known universe. If you enjoyed this video, please do me a huge favor and smash that like button. It really does help the channel grow, and it lets me keep making content like this for you. And if you have not subscribed yet, what are you waiting for? Hit that subscribe button and turn on notifications so you never miss a new video. We have got so much more incredible cosmic content coming your way. Drop a comment below and let me know which disturbing planet shocked you the most. Was it the diamond lemon world, with its pure carbon atmosphere? The lava hell planet that refuses to lose its air? The iron rain planet where metals fall from the sky? Or something else entirely? I want to hear your thoughts. Thanks so much for watching. Sweet dreams tonight, knowing that somewhere out there, a lemon-shaped planet is raining diamonds in the shadow of a dead star that spins 300 times a second. Pleasant thoughts, right? I will catch you in the next one.